In this video, we are going to look at exponential growth. Exponential growth is any quantity that grows or declines at a rate proportional to itself. So exponential growth, exponential decay. Exponential decay can be considered growth in the negative direction, so a decay. So exponential growth is any quantity that grows or declines at a rate proportional to itself. There are many different types of exponential growth. I listed a few examples here for you. Population growth can be an exponential growth. It can also decay. Interest earning in a bank account, for example, decay of radioactive materials. These are just a few examples. There's many different types of exponential growth or exponential decay. These are a few common examples. So let's write a formula for a population that is currently 46,500, and we want to increase by 2.4% each year. So this would be an example of a population growth. So we have 46,500 initially, and we want to increase by our 2.4%. So we have to think about this. If our population was going to stay as it was, we would have 100% of our population. So 100% of our population would stay as 46,500. But if we want to keep our full population, then we keep our 100%. But we want to increase by 2.4. So that means we need to add an additional 2.4%. So if we're increasing our population by 2.4%, that means the next year we would have 102.4% of our original population from the year prior. Now, if we want to do this for just 1 year, we could move our decimal, multiply by 1.024, and that will tell us for the next year. But this question is asking us to write a formula. So the formula means that we need to make something that will be perpetuated year through year through year. So all that we would need to do is change our year. So we'll start it with our population at time t. So t will be our years, p of t will be our population after a time t. If we have 46,500 to begin with, we need to change this to a decimal. So that would be 1.024. And if we change that to a decimal, then what we're doing is we're creating our, in this case, growth factor. So we have our 1.024. And then we need to do this every year. So this would be year 1. So this would be year 0. We would have 46,500. And then if we had another year, we'd have 1.024. And that would tell us after 2 years. And then another year, 1.024. And that would tell us after 3 years. Continuing to make these parentheses is not feasible. So what we can do is we can look at this and we can say that it's being raised to the power of however many years we have. So in our case, it would be raised to the power of t. So our formula then is going to look like 1.024 times t, where t is our years. So what happens if we decrease now? The first one was increase. What happens if we decrease? Well, we said that if we had our original population for 100%, then that would be staying exactly as it was at 46,500. When we wanted to increase, we added. So if we want to decrease, that means that our population is going to go down. So we want to take off our 2.4%, which means that we'll be left with 97.6% of our original population. Now, same idea, we need to take that and change it into a decimal. So that would look like 0.976. So same thing, our population at time t. Our population, t is our time. We would start with our original 46,500. And that would be our original, that's our original population. After 1 year, we would be looking at our 0.976. After a second year, we would have it times a second, a third, a fourth, a fifth as the years progress. So we'll raise it to our exponent of t, saying that however many years we're looking at progressing, we would replace t and then multiply through to find our population.